In this example, we're going to evaluate this indefinite integral, and we're going to do so by using integration by parts. So if this is something you would like to try on your own first, go ahead and pause the video and do so, and then come on back and we'll work the solution together. Okay, so in our integration by parts formula, we see that we have a u and a dv that we need to choose values for. And so let's go back to our original integral here. So if we chose the x as our u, that would be nice because when we differentiate that, the x would turn into just dx, or 1 dx. However, that would leave the dv as the arcsine of x dx, which we would need to integrate. So maybe let's avoid integrating this arcsine and instead say u equals this arcsine of x, and then so the dv would be x dx. Okay, so we'll differentiate here, and so we'll have 1 over the square root of 1 minus x squared. And then when we integrate the x, we'll have 1/2 x squared. Okay, so here are the terms and what we'll need for this integration by parts. So let's go ahead and slide up and we'll kind of put it all together. So this is going to equal uv. So we're going to go ahead and take these two rascals and multiply them together. So 1/2 x squared times that arcsine of x. And we'll subtract the integral, so we have v du, so it'll be these guys. So 1/2 x squared times, and then we have this 1 over that square root expression with our dx right here. Yeah, we don't want to forget that dx. Okay, so we have our work cut out for us here. This is what we'd like to do. So let's fix this integral up a little bit. Maybe bring this 1/2 out front. And then we have x squared over the square root of 1 minus x squared. Okay, so looking at this right now, well, we can't use a direct change of variables use substitution by saying u equals 1 minus x squared, because then it wouldn't cancel with this up here, and we'd end up in kind of a bit of a mess. So instead, let's try a different use substitution. And let's say x is going to equal the sine of u. Okay? Well, that means that u will be the inverse sine of x. And when I differentiate both sides, I'll have dx equals cosine u du. Okay, so that looks like some good stuff. So what can we do now for this integral? Well, the x squared, okay, if I square both sides here where my x equals this, I'll end up with sine squared u over, and we have the square root 1 minus, and of course the x squared was sine squared u, and the dx is going to be cosine u du. Well, alrighty, it looks like a lot of things can happen here. So we have a sine squared u times the cosine u over, so we can use a trig identity here. So 1 minus sine squared u is actually cosine squared u, but then it's the square root of cosine squared u, so it's just cosine u. Well, hey, that's nice because these cosine u terms will cancel. So we have negative 1/2 the integral of, well, just sine squared u du. Okay, well, how can we integrate sine squared u? Well, let's go ahead and use a power reducing formula on this. So instead of having sine squared, we can just have sines and cosines, and specifically just cosines. So sine squared u can be rewritten as 1 minus cosine 2u all over 2. Okay, well, this 2 in the denominator can be brought out front, so we could say minus 1/4. So the integral, 1 minus cosine of 2u du. Well, this isn't so bad at all. So we have minus 1/4. And so the integral here, the integral of 1 with respect to u is just u. And then the integral of cosine is sine, but we have to use kind of backwards chain rule here. So this is going to end up being negative 1/2 sine of 2u. And we could say the plus c in there as well. Okay, so we've done a lot of work through here, but remember we had this original piece here. So let's go ahead and bring this guy down. And so what he was, let's see, 1/2 x squared times the arcsine of x. Okay, so we can distribute through here, and we'll have 1/2 x squared arcsine of x minus 1/4 u plus 1/8 sine of 2u plus c. Well, since we had a change of variables, we did a little u substitution here. It seems like we need to put the values in terms of x back in. So we had a u right here and a u right here. So 1/2 x squared. And all the rest of this stuff just comes on down. Okay, so here's our first u. And that's going to be just that inverse sine of x plus 1/8 sine of, okay, now it's going to get interesting, 2 times the inverse sine of x plus c. Well, now we have quite an interesting situation here. All right, remember that these arcsines, these are actually angles, and so it looks like we have a double angle for sine. And remember that the double angle for sine, I'll go ahead and write over here. So when we have this double angle, it's actually going to be 2 sine x cosine x. Okay? So let's go ahead and employ that and see what we have. So we'll have plus 1/8. So it'll be 2 sine of our angle times cosine of our angle. Okay. Well, the sine of an inverse sine of x, well, those just cancel, and I'm just going to be left with x. So this will be 1/8 times 2x. But when we have the cosine of this angle, okay, well, let's draw ourselves a little right triangle here. And we'll say here's theta. And so if we're dealing with sine, and sine is x, we know that's opposite over hypotenuse. So then this other side will be the square root of, well, 1 squared minus x squared. And so cosine of our angle now is going to be the square root of 1 minus x squared over 1. But the over 1 we can just ignore. So here's what this looks like, and the 2 and the 8 we can do a little canceling with. So final value here, I'll kind of bring it up a little bit more. So 1/2 x squared times the inverse sine of x minus 1/4 times the inverse sine of x plus, looks like 1/4 x times the square root of 1 minus x squared plus c. And so here is going to be that integral, beautiful as it is, for our original integral expression right here. So the integral of x, arcsine x, is going to be this rascal right here. And we used integration by parts as well as a change of variables using a trigonometric substitution, and then a little trig identities and some trig right triangles right there. So again, here is that solution.